In probability theory and statistics, the chi-squared distribution with k degrees of freedom is the distribution of a sum of the squares of k independent standard normal random variables. A special case of the gamma distribution, it is one of the most widely used probability distributions in inferential statistics, for example, in hypothesis testing or in construction of confidence intervals. When there is a need to contrast it with the noncentral chi-squared distribution, this distribution is sometimes called the central chi-squared distribution. The chi-squared distribution is used in the common chi-squared tests for goodness of fit of an observed distribution to a theoretical one, the independence of two criteria of classification of qualitative data, and in confidence interval estimation for a population standard deviation of a normal distribution from a sample standard deviation. Many other statistical tests also use this distribution, like Friedman's analysis of variance by ranks. History and name. This distribution was first described by the German statistician Friedrich Robert Helmut in papers of 1875–1876, where he computed the sampling distribution of the sample variance of a normal population. Thus in German this was traditionally known as the Helmut or Helmut distribution. The distribution was independently rediscovered by the English mathematician Karl Pearson in the context of goodness of fit, for which he developed his Pearson's chi-squared test, published in, with computed table of values published in, collected in. The name chi-squared ultimately derives from Pearson's shorthand for the exponent in a multivariate normal distribution with the Greek letter chi, writing a 1/2 ir squared for what would appear in modern notation as a 1/2 x tib 1x. The idea of a family of chi-squared distributions, however, is not due to Pearson but arose as a further development due to Fisher in the 1920s. Definition: if Z1, Zk are independent, standard normal random variables, then the sum of their squares is distributed according to the chi-squared distribution with k degrees of freedom. This is usually denoted as the chi-squared distribution has one parameter, a positive integer that specifies the number of degrees of freedom. Characteristics. Further properties of the chi-squared distribution can be found in the box at the upper right corner of this article. Probability density function. The probability density function of the chi-squared distribution is where I, k/2, denotes the gamma function, which has closed-form values for integer k. For derivations of the PDF in the cases of 1, 2 and k degrees of freedom, see proofs related to chi-squared distribution. Differential equation. Cumulative distribution function. Its cumulative distribution function is where I cubed, s, t, is the lower incomplete gamma function and p, s, t, is the regularized gamma function. In a special case of k equals 2 this function has a simple form. And the form is not much more complicated for other small even k. Tables of the chi-squared cumulative distribution function are widely available and the function is included in many spreadsheets and all statistical packages. Letting, Chernoff bounds on the lower and upper tails of the CDF may be obtained. For the cases when the tail bound for the cases when, similarly, is for another approximation for the CDF modeled after the cube of a Gaussian, see under noncentral chi-squared distribution. Additivity. It follows from the definition of the chi-squared distribution that the sum of independent chi-squared variables is also chi-squared distributed. Specifically, if xi equals 1n are independent chi-squared variables with ki equals 1n degrees of freedom, respectively, then y equals x1 plus a plus xn is chi-squared distributed with k1 plus a plus kn degrees of freedom. Sample mean. The sample mean of NIID chi-squared variables of degree k is distributed according to a gamma distribution with shape I plus or minus and scale I parameters, asymptotically, given that for a scale parameter I plus or minus going to infinity, a gamma distribution converges towards a normal distribution with expectation I1/4 equals key invariance I2 florins equals key 2, the sample mean converges towards. Note that we would have obtained the same result invoking instead the central limit theorem, noting that the expectation of the IR squared is k, and its variance 2k. Entropy. The differential entropy is given by where I, x, is the digamma function. The chi-squared distribution is the maximum entropy probability distribution for a random variate x for which and are fixed. Since the chi-squared is in the family of gamma distributions, this can be derived by substituting appropriate values in the expectation of the log moment of gamma. For derivation from more basic principles, see the derivation in moment generating function of the sufficient statistic. Noncentral moments, the moments about zero of a chi-squared distribution with k degrees of freedom are given by cumulants. The cumulants are readily obtained by a power series expansion of the logarithm of the characteristic function. Asymptotic properties, by the central limit theorem, because the chi-squared distribution is the sum of k independent random variables with finite mean and variance, it converges to a normal distribution for large k. For many practical purposes, for Ka-50 the distribution is sufficiently close to a normal distribution for the difference to be ignored. Specifically, if Zai are squared, k, then as k tends to infinity, the distribution of tends to a standard normal distribution. However, convergence is slow as the skewness as in the excess kurtosis is 12 per carat. The sampling distribution of Ln, I2, converges to normality much faster than the sampling distribution of I2, as the logarithm removes much of the asymmetry. Other functions of the chi-squared distribution converge more rapidly to a normal distribution. Some examples are, if x to I is squared, k, then is approximately normally distributed with mean and unit variance. If x to I is squared, k, then is approximately normally distributed with mean and variance. This is known as the Wilson-Hilferty transformation. Relation to other distributions. As if then has the chi-squared distribution, as a special case, if then has the chi-squared distribution. If and, then. If then is an exponential distribution. If then, the chi-squared distribution is a special case of type 3 Pearson distribution. If and are independent then, is a transformation of Laplace distribution. If then, chi-squared distribution is a transformation of Pareto distribution. Student's t-distribution is a transformation of chi-squared distribution. Student's t-distribution can be obtained from chi-squared distribution and normal distribution. Noncentral beta distribution can be obtained as a transformation of chi-squared distribution in noncentral chi-squared distribution. Noncentral t-distribution can be obtained from normal distribution and chi-squared distribution. A chi-squared variable with k degrees of freedom is defined as the sum of the squares of k independent standard normal random variables. If Y is a k-dimensional Gaussian random vector with mean vector I1/4 and rank a covariance matrix C, then ZA equals a I1/4 TCA1, I1/4 is chi-squared distributed with k degrees of freedom. The sum of squares of statistically independent unit variance Gaussian variables which do not have mean zero yields a generalization of the chi-squared distribution called the noncentral chi-squared distribution. If Y is a vector of KID, standard normal random variables and A is a K-idempotent matrix with rank Kn, then the quadratic form YTAY is chi-squared distributed with Kn degrees of freedom. The chi-squared distribution is also naturally related to other distributions arising from the Gaussian. In particular, Y is F-distributed, YA F, K1, K2, if where x1 AAI are squared, K1, and x2 AAI are squared, K2, are statistically independent. If x is chi-squared distributed, then is chi-distributed. If x1 AAI2 K1 and x2 AAI2 K2 are statistically independent, then x1 plus x2 AAI2 K1 plus K2. If x1 and x2 are not independent, then x1 plus x2 is not chi-squared distributed. Generalizations: the chi-squared distribution is obtained as the sum of the squares of k-independent, zero mean, unit variance Gaussian random variables. Generalizations of this distribution can be obtained by summing the squares of other types of Gaussian random variables. Several such distributions are described below. Linear combination: if Ri chi-square random variables and, then a closed expression for the distribution of is not known. However, there exists a computationally efficient algorithm to calculate the PDF to arbitrary precision. Chi-squared distributions, noncentral chi-squared distribution. The noncentral chi-squared distribution is obtained from the sum of the squares of independent Gaussian random variables having unit variance and non-zero means. Generalized chi-squared distribution. The generalized chi-squared distribution is obtained from the quadratic form ZA squared where Z is a zero-mean Gaussian vector having an arbitrary covariance matrix, and A is an arbitrary matrix. Gamma, exponential, and related distributions. The chi-squared distribution ZAI squared, K, is a special case of the gamma distribution, in that ZAI, K2, using the rate parameterization of the gamma distribution using the scale parameterization of the gamma distribution, where K is an integer. Because the exponential distribution is also a special case of the gamma distribution, we also have that if ZAI squared, 2, then ZA exp, 1/2, is an exponential distribution. The Erlang distribution is also a special case of the gamma distribution and thus we also have that if ZAI squared, K, with even K, then X is Erlang distributed with shape parameter K/2 and scale parameter 1/2. Applications. The chi-squared distribution has numerous applications in inferential statistics, for instance in chi-squared tests and in estimating variances. It enters the problem of estimating the mean of a normally distributed population and the problem of estimating the slope of a regression line via its role in unregistered trademark ST distribution. It enters all analysis of variance problems via its role in the F distribution, which is the distribution of the ratio of two independent chi-squared random variables, each divided by their respective degrees of freedom. Following are some of the most common situations in which the chi-squared distribution arises from a Gaussian distributed sample, if x1, xn are id, n, I1/4, I2 florins, random variables, then where. The box below shows some statistics based on I1/4 normal, I1/4 I, I2 florins I equals 1, a, k. Independent random variables that have probability distributions related to the chi-squared distribution. Table of I2 value versus p-value. The p-value is the probability of observing a test statistic at least as extreme in a chi-squared distribution. Accordingly, since the cumulative distribution function for the appropriate degrees of freedom gives the probability of having obtained a value less extreme than this point, subtracting the CDF value from 1 gives the p-value. The table below gives a number of p-values matching to I2 for the first 10 degrees of freedom. A low p-value indicates greater statistical significance, that is greater confidence that the observed deviation from the null hypothesis is significant. A p-value of 0.05 is often used as a bright line cutoff between significant and not significant results. See also. References. Further reading. External links. Haswinkel, Mikhail, ed., Chi-squared distribution, Encyclopedia of Mathematics, Springer, ISBN A978-1-55608-010-4, Calculator for the PDF, CDF and quantiles of the chi-squared distribution, earliest uses of some of the words of mathematics, entry on chi-squared has a brief history, course notes on chi-squared goodness of fit testing from Yale University Stats 101 class. Mathematica demonstration showing the chi-squared sampling distribution of various statistics, for example I-XA squared, for a normal population, simple algorithm for approximating CDF and inverse CDF for the chi-squared distribution with a pocket calculator.